Alright, we've got a truss we're given here, and it is a simple truss. Okay, we got a pin support at A, we got a roller support at D. It's got two forces applied to it. You've got a 425 kilonewton force, and it is at a 110 degrees to the AB member. And you also have a force on joint C going straight down of 775 kilonewtons. All right, you also know that there are no distances here. All right, but we do have triangles, 30, 60, 90 triangles there. So what we'll do is we'll just make some assumptions on the distances. So for the member CB, one in the center there, we're going to assume that to be 1 meter. Okay, because this is a 30-60 triangle, that results in member AB being 2 and member AC being 1.732. Okay, so we're going to use that because we're going to have to solve for the force resultants, and we need to use those distances so we can use the summation of moments to get all our forces. All right. So what I want you to do is go ahead and solve for all the force resultants. But before we do that, let's take a look at that force 425 kilonewtons there. Let's go ahead and break that up into its component forces. So go ahead and pause the video here and break that up into its X and Y components. Alright, now let's look at how we solved for that. Okay, and so I drew a little sketch off to the side here showing the interaction between that force and the member. So it's at a 110 degrees to that member AB, but to the vertical y-axis, you know, that's 60 there because it's a 30-60 triangle. That relieves that that little skinny angle there as 10 degrees, so that the force component in the y is cosine of 10 times 425, and the sine of 10 times 425 is the y, or the x component. So that results in a y component of 418.54 and in the downward direction, and 73.8 in the direction to the right. All right, now that we got that, let's go ahead and sketch up our free body diagram for this truss system using dots to represent the joints, and go ahead and label all of them with angles, and let's go ahead and put the reactionary forces and solve for those at both A and D. Go ahead and pause the video. Alright, so now let's look at the reactionary forces. So what I did was I took the summation of the moments at A and was able to solve for D. And we got 618.1 kilonewtons up. Then next we took the summation of the forces in the y and was able to solve directly for the y component and got 575.4 kilonewtons in the upper direction. Next I took the summation of the forces at D, okay, as a check. But you also note that I jumped and indicated what the forces in the X were. I didn't even do that because there's only one force in the X, and I did that by what we call inspection, and therefore was able to report that A sub X is equal to 73.8. I mean, if you want, you can go through that, but it's pretty evident by just looking at that, and it's perfectly acceptable, especially when you only have one force applied and then one force directly. So that results in A sub X equals 73.8 kilonewtons to the left. Alright, so back to our check there, summation of moments about D. Did the check, so it should equal to 0, and it gets really, really close, which if we were to round everything up to the whole numbers, it would, so that worked out well, and therefore checks. Alright, the next thing we want to do is to identify what we need to solve for this. So we've got members, forces in AB, AC, BC, BD, and CD we want to solve for. Alright, so we want to attack this truss by focusing on an area where we can have only two unknowns, okay? Because we're using the summation of forces in X and Y. when we're solving for these joint problems, so we must have only two unknowns. So go ahead, pause the video, look over it, and determine what areas we can attack first to get it. Alright, now that if we look at this truss, there are only two really approaches we can do, because if we look at it, if we look at point, the joint at A, okay, we can work there because we've got only two unknowns. That's members AB and AC. And we could also do it at joint D because again we've got two unknowns. Okay, but joints B and C we cannot. Okay, they got too many unknowns. So we're just going to start with joint A. Okay, and what we're going to do here is we're just going to sketch it out. Okay, and here I'm just using blue to represent the known forces. So those are reactionary forces. And we've got a 73.8 to the left and 575.4 straight up. And what we're going to do here is we've got the first, I draw on the lines representing force AB and BC, and then we got to do a direction. Normally we assume it to be in tension. That's what I did for AC. It's in tension. And also you can note that yes, it makes sense because I've got 73.8 to the left, so AC has got to be the right. So when you're drawing a member, a two-force member in tension, it will be away from the point. Now, AB, normally I would draw it always assuming tension, but in this case I know it's in compression because the only Y component I have here is going up, which is the known force, so I have to oppose that, so I'm drawing AB in compression. Okay, so AB is drawn in compression and therefore is pointed towards the joint. Okay, so I'm going to start with the with that. Okay, so go ahead and pause the video and then let's solve for AB and BC. Alright, now I used the summation of forces on the Y as my starting point because of the two unknowns. Only one of them has a Y component, and that resulted in AB being 1,150.8 kilonewtons, and it's in compression. I note it with C. Then I attack it with the summation of forces X, and we get AC, and it's a positive number, and therefore I guessed correctly, which is tension, and I got 1,070.4. So now I'm going to move along, and I'm going to attack joint C. I'm going to move left to right. Now I can solve C because it now has only two unknowns, because I know AC, or in this case CA. Okay, so I'm going to isolate that joint. I'm going to draw it out again. I like to write a letter in the upper left there indicating that. And I'm going to quickly solve this one, because this one can be solved with very little math, because all we're doing is by observation, because the two unknown forces, CB and CD, are strictly in the Y and the X. So we can solve by inspection and surmise that CB is 775.0 kilonewtons in tension, because it's moving away, and CD is 1,070.4. Okay, and that is in tension as well. All right, so now I'm going to keep going. I'm going to move from C and I'm going to go to D. And again, I'm going to isolate that joint. I'm going to write in all my knowns. In this case, it's going to be the reactionary force D. And now it's our tension force CD. And again, it's always drawn away from the particle. So that I drew that there, indicate the angle. And you'll note that I am assuming dB in this case is in compression, because again, it has to move and oppose those forces applied in blue that we know about, and so it has to be in the downward direction. And so I can use the summation forces in X or Y and get the same answers. I do both of them, and you notice they end up being pretty close together. Alright, now I'm going to jump to, since now we have solved for all the forces, and you can look at them here. This is the solution. I boxed it. But what we want to do next is we are going to jump to B, okay, joint B there. And I'm just going to put in all the forces that we know, okay, because we solved for everything. So let's look at B in isolation. We got the resultant force broken up, 418.54 down, 73.8 to the right. And then I'm going to add the forces BD, BC, and BA. Okay, and we know those values. I'm going to write them in there. So I've got those in there. So BA is in compression, and BC is in tension, and BD is also in compression. Okay, so now I put those on there, and I'm going to solve for the forces in the X, and look, I got almost 0, so it's approximately that checks. And I do the summation of the forces in Y, and look, almost 0, so that's good. So both those check. So therefore, I've gone through now, and I've analyzed every joint and came up with every member that you can calculate, and I just summarized it in spots. Sometimes what they'll ask you to do on some of these truss problems is to write it down on top of the truss, your free body diagram, but that can get a little crowded, so just boxing the answers as such is acceptable.